Yeah, today is the last lecture in the series for reinforced concrete design or RC1. I'm going to go over example of single column footing and combined footing. So hopefully I will be able to cover two examples. The first one will be design of single column footing. So we have a column. I have two statements. We have a square column. (18" service dead load SDL, service dead load equal 400 kips, and the service live load equal 270. Fy equals 60 KSI, F prime C equal 5 KSI, Fy equals 60 KSI. This is for the column, which we're not going to design. For the footing, F prime C equal 3 KSI. By the way, it's common practice to use lower strength for the footing compared with the column concrete. So 3 KSI is the smallest concrete you may ever have, which is 21 megapascal. Usually it's easy now to achieve the 4 KSI. Okay, this is just a sake for this example. However, sometimes you may design a column like that. You may design a footing like that, sorry. Q allowable equal 6,000 PSF or 6 KSF. The level of the footing is 6 foot below grade. 6 foot below grade. Design a square footing or a single column footing for this square column. Any question? So usually, guys, when you do any analysis in a building, usually when you run your analysis, always run your analysis from the service loads and the columns. When you give the column loads, try to give the service loads. Why? Because we use the service load to calculate the area of the footing. We use the service load on the column to calculate the area of the footing. Once we have that area, okay, we magnify the load for strength design. Again, now the word strength design should be a familiar term for you. Strength means shear, strength, flexural strength design. Okay? So, as we said, the column is 6 foot below grade. Usually, this is Q allowable. That's from the soil report. That's from the soil report. They calculate that, or they find that, or they test that. The bearing capacity of the soil at 6 foot was 6,000 PSF or 6,000 pounds per square foot or 6 kip per square foot at that level. So there is going to be the self weight of that. If it's 2 foot, 3 foot, that's going to be concrete height, and the rest will be soil. If you can assume, again, you can assume the density or the unit weight of the soil is 100 to 110 okay, PCF. We know the concrete is 150 PCF. As I told you, take an assumption of that area and mix an average weight between concrete and soil. So you can take 125 PCF, pounds per cubic foot, as the weight of the material on top of the footing. To calculate the effective bearing capacity as follows. So Q effective equal 6 KSF minus 6 times 0.125. Again, this 0.125 is 0.125 kb per cubic foot. Okay? That's the unit weight. So you multiply by the height, you get it in kb per square foot. You subtract from kb per square foot, how much you get?
5.25 kb.
So we have 5.25 KSF or kb per foot square. That's what's effective for supporting the load coming from the column. Now the second step is to calculate the area. To calculate the footing area. A equal the service load as is, not the factor. This plus that, which is 400 plus 270 divided by the effective 525. Equal.
Shouldn't that be 0.4 plus 0.270 divided by? Oh no, 36 kips. Never mind.
Yeah.
Sorry, kips.
Yeah. The service load is that, and service load. Okay. So this number will give you foot square. The area in foot square.
127.6.
127.6 foot square. Since it's a square column, there is no limitation on the length, on the width in one direction. Try to make it square footing. If there is a limitation on the width in one direction, so that's your maximum width you can use. We divide this one by that width. So if someone is telling you you can't have more than 5 foot in one direction, then the second side of the footing will be the 127 divided by the 5. But here we have no limitation. Nothing says you can't exceed that and that. So we're going to take the square root of that to get each side of the column, each side of the footing. How much you have?
11.3.
So you calculate 11.3 for each side. We will use 11.5 by 11.5 footing. So it's 11. Sometimes you can have 11 foot 6 inch if you want, or we will do that. 11.5. And this is your column, which is 1.5 by 1.5, right? 18 inch is 1.5 foot. That's your column, 18 inch, 1.5 by 1.5. In the center, again, the guys, the construction workers, they make sure it's exactly in the center. It's been take a lot of care when they put the center lines for the footings and the columns. Okay, guys. Now, once you have this area established, there's one more Q need to be calculated for a strength design, and that Q is calculated based on the factor of loads. These are common mistakes, guys. Some guys, they divide by 6 in here. Some guys may do it right, okay, they will get right. Now, when they want to calculate Q effective, they will divide the service loads by this area. Okay, so now Q effective, when you say Q effective, you subtract whatever on top. Q ultimate now, not Q effective, Q ultimate for strength design must be based on the factor loads. And the loads I have in here are dead and live. And we know the load combination that will control when you have these ratios for the dead between the dead load and live load is 1.2 dead plus 1.6 live. So Q ultimate will be 1.2 times 400 plus 1.6 times 270 divided by the actual dimensions that you will be using. You don't use this one anymore, the 11.3 he calculated from this, or some may say this, divide by that. No, this is the actual you will be using. So you divide by the actual. By 11.5 times 11.5. So Q ultimate equal 6.9 kb per foot square. KSF. Good? So far so good. Now what we need is the thickness now. Usually you guys in AutoCAD, you have to bring, you draw everything to scale. You bring these lines here, column. That's not in the center. Let's assume it's in the center. We do to scale. Okay, so we have that one, which is 11 and a half. And we have this one, 1.5. I have this dimension. I need to find the thickness, the depth. We need to find the depth. If we find D, we can calculate the final edge, because the final depth will be D, the effective depth, which we can calculate from the moment, plus 3-inch clear cover, plus about 1 inch for the diameter of the bars. Okay, plus 1 inch or 1.5 inch to the diameter of the top bar. Okay, if you take 1 inch will be good, because you may say, you know what, I know the top layer will control, but how about taking an effective D between the two? Because they will work, they both work together, because they are tied together. Okay, so 1 more inch will be enough. So usually in edge equal D plus 4. D plus 4. That's a good assumption. Okay, how we calculate D now? How we calculate D? See, in beams, we calculate the cross section D from the moment. In beams, we calculate D and B from flexural. Then we design for shear using stirrups. Now we calculate D based on shear. We calculate D based on shear. Then we're going to design the steel for that D. We said there is 2 types of shear in single footings. There's something called bunching shear, and there's something called one-way shear or beam shear. The bunching shear is an area along this area, which is D over 2 from the face of the column all around. So this perimeter or this area has this dimension, which is the column plus D over 2 from this side and D over 2 from this side. So it's going to be the column width, which is 18 inch, plus D, this one. Right? So we need to calculate something called B node for bunching shear. I told you, bunching shear control the depth of single column footing. Okay? But how in that value in the what's the shear strength? Phi BC bunching equal what? Remember? 175 square root of prime C times B naught D. B naught D. In the FE exam, sometimes they ask you what's B naught. What's B naught? It's the width of the column plus D from each side to get this one times 4. So B naught is the length of this parameter. It is this plus that, not the area. B naught is this plus that. So the width of the column plus D times 4 if it's square column. If it's not square column, you add each one of them. Easy, right? So it's going to be, this is B naught. So what's D? We don't have it. What's D? We don't have it. So this is the strength. We need to compare it with what? V ultimate that's acting on this. V ultimate that's acting if this piece is punched, is taken. I showed you. Right? I will show you how we calculate that. So that's from structural analysis. You will calculate V ultimate punching. You will compare it for that. In other words, you need to pick D that give you this one greater than V ultimate punching. Once we have that D, we will check the one-way shear which occurs. This is D over 2, we said, right? That shear occurs at this one here, which is D from face of the support. That's like the beam shear. It's called the beam shear, the one-way shear or beam shear. So here, again, what control is this here. So if you want, by the way, if you want, you can calculate. If you want, you can calculate VU2 in terms of D. VU punching in terms of D, and you can calculate this one also in terms of D. It will be a square equation. Then you make them equal. That's not practical. You can do it if you want. If you have a fast calculator, you can do that. then calculate the required width. Or just assume D. Your first assumption will tell you where you are. And sometimes there's some guidelines when the footing is 6 foot by 6 foot, it's like 1 inch or 1.5 inch. When it's go to 8, it's like 2 feet. When it's go to 10 or something, it's like 2.5 or 3 feet. So you can make an assumption. I'm just gonna do a random assumption. I'm gonna assume D equal 26 inch. Why? Why am I assuming 26 inch? Because I'm kind of saying H is 30 inch, which is 2.5. Okay? I'm going to assume this one and check. Why? Because at the end, I'm going to have my final thickness, which is D plus 4 inch. Okay? And let's check in here. If we have that, this side, which is the 4 sides, this side of B naught will be 18 plus D. D over 2 and D over 2. So it's going to be plus 26. That's one side. All of them are the same. So this times 4 will give me P naught in inch. So how much P naught? How much?
176. 176.
176 inch. That's P naught. So what's PVC now? With that P naught. PVC equal 175 times square root. Remember, now we're talking about what? No. Talking about 3,000. Talking about the footing. This is the footing concrete. That's for the column. Okay, be careful. Sometimes if you are required to design the column, then the footing, be careful with the concrete. So this 3,000 times B naught, which is 127, right? 176, sorry. Times D, which is 26. This will be in pound always. This equation will be in pound. You divide by 1,000 to get it in kip. So PVC equal
188 kips.
that much? Sure?
Seemed like a lot to me.
Not a lot. Is that what you get, guys? Yeah? Okay. Let's see. Now, what's VU2, as I told you? Look. You imagine when punching occurs, we will have 2 parts, right? We will have the column with that B naught thing as one piece, and we have the remaining footing with void. Nothing. You understand? So we have the remaining footing with that thing taken out. That footing has a bearing pressure of how much? Q ultimate. Right? So there is a Q ultimate from bottom. So what's resisting that Q ultimate? Shear inside that void. Right? Shear within that void. Okay? So that shear equal Q ultimate times that area. Right? VU that caused the punching is Q ultimate times the area of that footing, of the footing without that, which is the area of the total footing minus the area of that small thing. Again, I'm going to write it so you guys understand. So VU, sometimes they call it VU2 or VU1, one for the beam shear, one for the punching. Just call it P, punching, equal Q ultimate, which is 6.9, times the area, which is 11.5 times 11.5 minus, now you guys tell me, if you understood this one, you tell me what's the number now. What should I subtract? Is it 1.5 by 1.5? No, this area that will punch.
Plus.
will be
So it's going to be,
18 plus 26 square.
what's this side? We said
18.
18 plus 26.
So 44 square.
44, that's an inch. We divide by 12 to get it in foot. So how much is that?
3.67.
Minus 3.67 squared. You understand this? You see, in there we get the area. For the bunching force in here, we get the perimeter, you know. I'm going to draw it again here. So this is gun. This is gun. So wherever we have a pressure in here, which is a Q ultimate times this area, all of it, minus the pressure times this area, which is, this one is 18 plus 26, an inch. This is what I did here, which is 3.67. How much is that?
119.
119?
820. 820.
What's the number?
820.
8?
20. 820.
Sure?
6.9.
Yeah, 820. So RV ultimate is way, way, way greater than RV. I'm redoing the VC.
Oops, I switched. Do you multiply by the 26 in here?
Yes. Yes, that's 188. That's right, and this is 820. So we need a much, much bigger footing.
That's what we see in here. I'm just lower as a wave. Fair enough.
So do we try D at 50 inches? Is that what we do now?
Andrew, not awake. The guys who were in Chicago. He was not there, so he should be awake. Is that the right formula I said for the shear? I made a mistake in there.
Should that be in inches or in feet?
Wait. If it was a beam shear, don't we used to have, where is that? I made a mistake.
4.
This should be 4. For the beam shear was 2 square root of prime C. So again, correct that because I erased that. PVC for punching equal phi times 4 square root of prime C B naught D.
Still not good.
I missed the 4.
Still not good.
Yeah, we are close now.
Okay.
But that cannot be that mistake. Okay? So how much is that now? Guys, correct this one. Whoever is watching.
752.
So there's a 4 in here. See? 752. We are close.
Okay.
We are close. Okay? I'm gonna now, this is greater than PVC, P, no good. Try D
35.
equal, no, I don't want to go 35. 32. We'll be fine with that. We will be fine with that. So that I have a 3-foot depth of footing. If that's the case, you go back with all these calculations. VU will change. VU will change. It will be 32 plus 18, whatever number in here. Give me those two numbers, guys. VVC and VUP. So you will have V naught here will become 18 plus 32 times 4, that's your V naught, and remember D also will change to 32, so those will change. Did you get the number for PVC?
Yeah, but it's like 1,000 now.
Yeah, good.
1,051.
Got the same number? Looks fine to me. You get that? Someone confirm, please. I need another one to confirm. It's just numbers. Okay, we'll do it all together. 18 plus 32 times 4 times 32 times square root of 3,000 times 4 times 0.75. That's another number.
I got it.
You got this one?
No, you didn't.
What? That's why the questions must be multiple choice in any engineering course. To be honest, an engineer must be able to get a correct answer. It's just numbers, numbers. Again. Maybe you multiply by 26 in here.
I multiplied by 32.
So, okay, how much this number will be? 18 plus 32.
It is 951. It's 44.
951 or 1051?
925. I can't believe it. 925? It is 925.
Laura,
Yeah,
still steaming.
I don't know.
925. So VU now will be, look at this one. So how much this one was? The new one. This one. What's this one? 32 plus 18 times 4. Divide by 12 to get it in foot.
32
17, 16, 16.6.
Multiply them together. That's the square.
You said divide by 12.
Yeah.
That's
18 plus 32 divided by 12.
4.1.
4.1. Do this number for me now. 11.5 square minus 4.1 square times 6.9. So you get 793, we are good, right? Wait, before we go, by the way. 793, good. So this thing is good. By the way, before we go, look, if this one was 4,000 psi concrete, if you are a designer, you're starting things from scratch, you put the specification for that. If this one was 4,000, with the 26 as is, how much you get, by the way? This one was 40,000. So, square root of 4,000 times 176 times 26 times 4 times 868. That will do it, by the way.
Yeah, just barely.
That will do it. So, and it's easy to get 4,000 psi concrete. Okay, just to let you know when you go out and work.
Is 3,000 cheaper? Is that why they do it?
It's not cheaper. Sometimes they don't trust the workers and they assume the concrete may have some tag and in the future will have degradation. It's easy now to get the new days. It's easy to get 4,000. Easy. Okay. So we are good. So that's our D, and we expect our footing thickness to be 3 feet. 3 feet thick. What's the next step now? Check the beam shear. We need to check the beam shear. The beam shear, guys, will be this segment. This segment of the footing sheared at D from the face of the column. This segment sheared. So the pressure is all under. So this side here, from the inside, will have the beam shear strength, which is this side. The beam shear strength is what? PVC. Beam or shear, sorry, beam shear. Equal what? That's the old one. 175 times 2 square root of prime C BD. Not B naught, BD. This is the classical one. We took it in beam design. Okay? So this one must be compared with what? With the Q ultimate times this area. This area is the width. 11.5 foot. So how much this one, this side here? We said this is this. This width, which is a D from the face of the support, a D from face of the support. So how much is this one? Okay, to the face of the support, look, if we subtract the column, we have 11.5 minus 1.5, that's 10. So that's 5, right? Subtract D from there, you get this width. So this would be, I would say that you can say, it's 5 minus 32 divided by 12. So they are saying 2.33, which is 5 foot minus D, which is 32 inch, you change it to foot over 12. So they get this. Good? Now Q ultimate times this area, which is 2.33 times 11.5, that must be resisted by this strength in here. Good? So VU beam shear, VU beam shear equal Q ultimate is 6.9 times 11.5 times 2.33. What's the number?
184.
So this is 184 kil. Now what's this guy in here now, the strength that we have? 175 times 2 square root of 3000 times what's B? What's D? Oh, I'm gonna do it here. Need to be verified. So it's gonna be 0.75 times 2 times 3000 times, no one is saying what's B, times D is 32. This is in inch, everything must be in inch in there and pound. We divide by 1000 to get it in kil. So what's D? What's B? You just think. What that shear stress, you know what's this one here? 2 square root of prime C. That's the shear stress. BD is the area, is the shear area. So what's the shear area? That's D and that's B. Right? So this equation, 2 square root of prime C, BD, 2 square root of prime C, that's the shear stress. Times the area that the shear stress is acting on. So this will be huge, right? It's 11 times. So it's 11.5 times, how much? 11.5 times 12? 138. This 138 inch, that's B, which is 11 foot times 12 to change it to inch. So you got VBC, how much? 63? 3, that's a good number. 363. Okay, way bigger than VU1. I told you, single column footing beam shear is secure because D is determined based on punching. But you have to check it. For some cases, it may not work. You have to check it. Okay? In combined footing, this is what control the design. The beam footing control the design. Combined footing, there is more than one column. So you get D from the beam shear. Then under each column, you assume that column by itself will punch. Then you check punching for each column by itself. Is this good? Okay. So now we have D. The only thing that's left is what? Reinforcement. We need to design the reinforcement. So we need to calculate the ultimate moment, the maximum moment, and design. So this is my footing.